In this video, I want to explain how I think about the process of determining whether a subset of a vector space is a subspace of that vector space. Or in other words, given a subset, is it actually a subspace? There are three things we need to check to see if something's a subspace. The whole idea of a subspace is that we have a subset within a vector space, and we want to know, is it itself a vector space? We had this whole list of 10 vector space axioms that I'm not even going to put up on the screen because we don't need them here. Most of those axioms are already satisfied by the fact that we're living in a different vector space. And so we know that addition, for instance, is associative. All we need to check is that our subset contains the zero vector, is closed under multiplication, that is to say, when I multiply any vector in the subset by a scalar, I land back in the subset, and that is closed under addition. Not what I meant to do. In other words, that if I add two vectors in the subset, I'll get a third vector that's in the subset. There are two steps to this process because I don't know what the answer is supposed to be. First, I have the experimentation step. This is where I try to figure out what the answer is. Try to kind of justify to myself, is this thing a subspace or not? And then there's the proof/justification part where I actually write out an explanation for why this thing is or is not a subspace of the vector space that we're talking about. Let's look at an example. So here we have a subset of R3. So these are the set, I'm looking at the set of vectors in R3 such that when I multiply the three coordinates, I get 0. I want to know, this is a subset, right? All of these things are in R3, but is this a subspace? Does it contain 0? Is it closed under multiplication? Is it closed under addition? So my first part of what I need to do is the experiment part. And let's quickly look. So in the experiment part, what I'm going to do is I'm going to look at a few things. So the first thing, I'll jump back and forth a little bit. The first thing I'm going to do is I'm going to check if 0 is an element of the subset. This is usually the easiest thing to check, and if it's not, it can be done really quickly. So let's check if 0 is an element of our subset. Well, we're in R3, and so if I look at 0, and I multiply the three coordinates, let's call this thing S, right? So that I don't have to keep referring to it in some weird way. This means that the 0 vector is an element of S. All right, so that was just the first thing to check, right? If 0 wasn't in the subset, it would definitely not be a subspace. All right, so the next thing I want to do, and this is a really important step in experimenting, we don't want to jump ahead to just doing stuff. It can be tempting to just start adding vectors, start multiplying vectors to see what happens. We want to make sure that we write down a diverse collection of elements of the set. And what it means by diverse will hopefully be made clear when I start writing down some examples. So let's write down some elements that are in S. Well, I have the 0 vector, right? We already saw that. So that's one element, 0, 0, 0. And I'm just going to write down a bunch of things. So I want to write down things that multiply to 0. This is a good example. This is a good example. And I could keep writing down elements. Hopefully you're seeing the pattern of how I'm writing these, but I'm not writing down a diverse collection of elements right now. Yeah, I'm writing down a bunch of elements, but it's not a contest to write down as many elements as quickly as possible. The goal is to have a diverse set of elements. And what does diversity mean in general and in this context? It means that they don't all have one defining characteristic that isn't true of the set as a whole. right? If we said that a bunch of examples were not diverse, and this would apply in kind of whatever setting you're talking about diversity, what you mean is that they possess some characteristic that's not always true. For instance, here, these examples all have zeros in the second and third entries, but that's certainly not necessary. So I'm going to write down some more examples that don't do that, right? So like 0, 3, 5, 1, 0, 2, 7, 3, 0. So now we're getting a bit more diversity here, right? We're writing down examples that aren't just kind of all copied versions of each other. But I'm still missing something. And I don't even know whether this will matter in this problem. I don't think it does. Maybe it does. It's important to think about things that you've forgotten to do. And the most common thing to forget is negatives, right? All of my elements so far, I've written down just positive numbers. So let's include some negatives. All right, so now I'm feeling pretty good. And then you might stop and say, wait a second, but you still are missing something. You haven't combined negatives and positives. All right, so I'm going to stop there. But hopefully this makes sense, that it's important to write down a bunch of elements first. And it's important that when you're writing down the elements to not just do this. You want to think about, am I actually representing all different types of elements that can be in this set? Okay. What's next? Well, we wrote down a diverse collection of elements of the set. We might need to come back to that, right? Maybe we'll decide, hey, we actually missed something. I'm going to check scalar multiplication. And so by check scalar multiplication, I mean, I'm just going to start multiplying things by scalars. And I have my elements here, so let's just choose an element. And I'll multiply it by something. I'll multiply 2 times, I don't know, 3, 0, 0. This resulting element is in the set, right? 6 times 0 times 0 is 0. And I could do something like 5 times minus 3, 7, 0. And I can confirm that this is an element of the set. When I multiply the coordinates, I get 0. Now, it's important, don't forget about negatives with the multiplication, right? We had diverse elements of the set, but when you're doing multiplication, you have to choose diverse things to multiply by. So let's not forget about that. So let's do like -3 times, I don't know, -1, 0, -5. So I check some things, and so far when I've multiplied by scalars, I end up with elements that remain in the set. You should always not just be thinking about the examples you're writing down. You should be thinking more generally about what's going on and why it's happening. And I mean, as you were writing down examples of elements of S, if you did this on your own, you maybe got to the point where you quickly remembered, look, for 3 numbers to multiply to 0, at least one of them has to be 0. And so when I'm writing down elements of S, I'm really just thinking about, look, I'm just writing down lists of 3 numbers where at least one of them is 0. And then with multiplication, you hopefully start to notice, look, I'm multiplying by a scalar doesn't change the fact that I have a 0 in this list. So multiplication is actually not going to be an issue. That is, this set is going to be closed under multiplication, so I'm going to move along. That's one, I've confirmed that I have 0 in the set, and that, I think anyway, this set is closed under scalar multiplication. All right, now I have to look at addition. I have to add pairs of elements and check if the resulting elements are in the set. Keep doing this for some reason. All right, so that's where we are right now. And I'll point out steps 3 and 4 can be done in either order. It doesn't matter whether you check multiplication or addition first. I just put it in some order because I had to choose some order to write them in. All right, so I'm going to quickly run into my next example, so we'll have to move stuff down. Let's look at addition. Let's choose kind of two early elements from the list. So I could add 1, 0, 0 and 3, 0, 0. I would get 4, 0, 0, and that's an element of the set. But as we're getting into this, I'm not just trying to write stuff down just to write stuff down. I want to be thinking about what I'm doing. And we already talked about how the issue, the thing that makes something an element of this set is that one of its coordinates is 0. And I'm starting to see how I could add things and not end up with 0 as a coordinate. For instance, I'm looking at these two. Right? If I am adding two vectors where the zeros are in different coordinates, I'm realizing something's going to happen. So I'm going to say something like, I forget what they were, not that it matters. When I add these two together, I get -2, -2, -5. But then when I multiply those numbers, I get -20. So I get something that's not in the original set. And this is really important. In this process of experimenting, if at any point you obtain something outside of the set, you need to stop. And so that's what I'm going to do. I've determined that this is not a subspace of Rn because I've added two elements that were in it. And I've seen that I got a third element that wasn't in it. So I'm stopping. I'm done with the experimenting phase. And I need to move along. So I need to move along to my proof/justification phase. Okay, let's go down and look at that. Proof/justification. Well, I found a counterexample. That's what it means when you find something that's not in the set. Either maybe I found that 0 wasn't in the set, or maybe I found that there was some scalar multiplication that took an element in the set and landed it outside the set. Here, what I found was that there were two elements that if I added them, I got a third element that wasn't in the set. So far, everything I've done, if I go back to the iPad, all of this stuff that I've done is not actually going to get written down. Let's say I'm writing an answer on an exam, or I'm explaining to someone whether this is a subset of R3. None of this goes into my justification. This is all work off to the side. This is all done on scrap paper, right? Writing down elements of the set, multiplying things, adding things. I was doing this for myself. Let's move this example somewhere else. I'm sure there's a way to add third page here, but let's for now just clear it off the screen. So far what I've done is not work that goes into my answer. And this is an important thing to understand, is that I did all this side work, and now I have to figure out how to write out my proof or my justification. I use those two words because I want you to think of proof as being a justification either to someone else or to yourself, right? And I want to write it out because when we write things out, we start to realize our flaws in logic. And so what I want to do is write a proof that my subset S is not a subspace of R3. And counterexample proofs are always, or not always, but in this context, are going to be really short. I don't need to mention that 0 is contained in S because I'm trying to show that it's not a subspace, right? I'm not trying to, I don't need to mention that it's closed under scalar multiplication. I need to present my counterexample. So I'll say something, and you could phrase this however you want. Note that these two elements are in S, but their sum is not. This means that S is not closed under addition. So S is not subspace of R3. When you find that something's not a subspace, your proof will be very short. And it will be very easy to understand. All of the work is in the background, right? I did all this work up here. All this hard work writing down elements, checking multiplication, even though it turned out that that was not really an issue, checking addition. All of that doesn't show up in this proof. The only thing that shows up in the proof is once I get to my counterexample. And you know, there's that kind of joke, right, that your keys are always in the last place you look, right, because you don't keep looking. Your counterexample is the last example you look at, right? Once you've found a counterexample, it's always the last thing you looked at, right, because you don't keep going. I found that this thing was not closed under addition, and I immediately stopped, and that's what my proof is. I present that example, and I add some words to explain what I'm doing, right? Just because I could stop right here and not include this last part, but it's better to be really specific. Look, I'm saying that it's not closed under addition. Okay, let's go to another example. And as you can guess, this is going to be an example of what happens when you actually do have a subspace. So here's the example that I had to move down. So this is example 2. And let's not call this thing S. Let's call this T, in case we want to come back and compare the two. I guess I should point out, I didn't say this already in the video, but I had meant to. These are subsets of R3. And so you might say, hey, let's look at some pictures, right? Let's try to look at some graphs of these things. That's almost always a valid thing to do. I actually find with this specific type of problem that it's usually not useful. That is, a lot of the time, you're dealing with a situation where you can't really visualize what's going on. And even when you can visualize what's going on, unless you know what a subspace looks like, which is something that we'll talk about later, there's not really value in graphing it, right? You've seen this before maybe in calculus classes where it's like you have a graphing calculator or you have Desmos, but it's not necessarily useful to graph things in certain situations. So here I don't actually think that that graphing is a useful way of visualizing. Our visualization is in writing down a lot of examples. All right, so I'm going to not hop back and forth between these pages, but I'll just show you them. I'll go back to our experimentation page just one quick time. So I'm not going to hop back and forth because we already went through it once, but we're going to check the zero as an element. We're going to write down a diverse collection of elements. We're going to multiply by scalars. We're going to add pairs of elements. And we're looking for something outside of the set. If at any point something's outside of the set, we stop, right? If we find a counterexample, it's always the last example that we looked at. Okay, so first we need to check 0. I don't know why there's a lot. Yeah, they were spell checking me. Well, this thing's in the set. Okay, I mean that's often the case, right? If they'd be really quick examples if they didn't contain 0, but we do have to check, and we should check first because it's the easiest thing to check. All right, now let's write down a diverse collection of elements that add up to 0. The 0 vector is often not useful to work with in examples. It doesn't really help you because if you add it to something, you don't change it. If you multiply it by a scalar, you don't change it, but I'm still going to write it down. I want coordinates adding up to 0. And I'm not just going to fall into the same trap I did last time. I'm going to start to realize, look, I can't just make everything be the first 2 coordinates. So let's do this. Right, write down things like this. And so far, I'm still falling into the same kind of trap, right? I don't actually, it's not required that I have a 0 as one of my coordinates. For them to all add up to 0, I can actually just write whatever I want for the first 2. And then the third coordinate will take care of itself. And I'll stop there. I'm not going to try to dwell too much on writing down more elements, but if I need more, I can write them down later. All right, so I'm going to check multiplication. I'm going to multiply by scalars. So for instance, if I do 2 times 1 minus 1, 0, get 2 minus 2, 0, and this is in the set. This is in T, right? Let's do a negative because I was supposed to, right? I'm writing stuff down that doesn't make sense. I got ahead of myself, right? It doesn't equal that. It equals this vector. And you can see that when I add these things, I'm going to get 0. And when you're writing down these sorts of things, you don't need to keep writing examples if you start to realize that your set's going to be closed under multiplication or addition. Because what I'm starting to realize is that when I multiply all of the coordinates by the same thing, I'm not going to change whether they add up to 0. And maybe you're not there yet. Maybe you're saying, wait, are you sure? And I would say, write down some more examples. You write down a few more examples. You start seeing, wait a second, this is always going to work this way. I want to move along. Because it could be that it's closed under multiplication, which is what's going to be the case. And no matter how many examples I write, I'm never going to find something that doesn't work. And so I don't want to waste time doing that. It also could be that addition is where things will fall apart. So let's see. Let's look at addition. Let's add some elements. So 1 minus 1, 0, plus 1, 5 minus 6 is 2, 4 minus 6, and these things add up to 0. Okay, I'm already getting this feeling, right? Let's see, we had 2 minus 3, 1. We had 0, 3 minus 3. I add these things up and I get 2, 0 minus 2. Okay. It's really looking to me like I'm not going to find a counterexample. And I could keep working because maybe there's something I didn't check. But I'm having this same sort of feeling where I say, look, if all these coordinates add up to 0 and all these coordinates add up to 0, when I add these things together, the resulting vector, all the coordinates are going to add up to 0. And so this is what I mean when I say if all the elements are in the set, look for patterns. Especially once you've realized that you think that the thing's a vector space, you think it's closed under multiplication and addition, the patterns are going to be what allows us to prove that this is true. Right? I noticed that I don't think that scalar multiplication or adding two vectors is going to change the defining property of the set. And so I think this thing is actually a vector space. So let's move on. Let's try to justify that that's true. And this is going to be much harder. This is the hard part of this whole thing. That is, it's going to be much harder than when we find a counterexample. So this is the hard example of proving something. So what do? I need to show that 0 is in the set. That's easy. But then I need to show that the set's closed under addition and that the set's closed under scalar multiplication. And right now I think it is. And I have some sort of hand-wavy justification. I think I was literally waving my hands while I explained why I thought it was true. I need to actually show that it's true. And so I want to do that in this example. So this is my proof that T is a subspace of R3. And notice, I didn't just start writing down this proof. I did a lot of work first. And again, that work is not going to show up in the proof. It's actually literally, other than the 0 vector thing, none of it's going to show up. Because it's not enough to show some examples, right? I can't just tell you these examples of scalar multiplication resulting in elements still in the set, an addition resulting in elements still in the set, and know that that tells us that all possible additions and all possible scalar multiplications will remain in the set. I need to show that that's true somehow, and this is hard. And so all of this work isn't going to directly help me, but it will allow me to understand how to prove this. So the first part is easy. So first I have to address 0. So the 0 vector, 0, 0, 0, satisfies the defining condition. So 0 is in the set. I don't know why I wrote this. I think in my proof justification I said to do addition before multiplication, but it doesn't matter. I'm going to stay in the same order as we did the experimentation with. This is where things get tough. I can't just write down one of these 2 examples. I can't write down both of these examples. I can't write down more examples. I can't write down any examples. Proof by example is not proof. What I need to do is I need to write down a generic scalar multiplication and show that a generic scalar multiplication results in an element still in the set. So what does a generic scalar multiplication look like? I'm going to say something like this. I won't say A because we've been using that to mean something. Yeah, so what should I make our scalar be? Well, I guess I'll just call it A. So I'm going to let A be an element of R. So A is a real number. I want V to be an element of T. So this is what I mean by a generic scalar multiplication. I'm taking any element of R and any element of T and I'm multiplying them together. But A being a real number, there's nothing more to say there. That just means that A is a real number. But V being an element of T means something. And this is why I was realizing that I didn't know what I was going to call my scalars. So I'll call V X, Y, Z. But this means something. Right? So I start with any element of R and any element of my set. And I say, what properties do I get from that? Well, I get that my vector has its coordinates adding up to 0. And now I want to look at this multiplication. A times V. Well, that's A times XYZ, which is AX, AY, AZ. And now I want to check that this is in the set. And I can do that by factoring out in A. And X plus Y plus Z is 0. This means that AV is an element of T. All right, so back through that again, because that was pretty fast, especially if you haven't done proofs at all, or if you haven't done a ton of proofs. I started with just any old real number and any old vector in the set. Then I said, look, being in this set is not just I'm a vector in R3. I'm a vector in R3 with this property. So I remind myself that's what it means to be in this set. And now what I want to check is what happens when I multiply any old real number by any old vector in T. Well, I get this. And I realize, hey, wait, if I add these coordinates, I factor out an A, X plus Y plus Z is 0, I get 0. So what I've shown is that taking any real number and any vector in the set, when I do scalar multiplication, I get something in T. And so I should add one more little bit, and T is closed under multiplication. when there's no chance of confusion, I often just say multiplication instead of scalar multiplication just to save a little bit of time and space. Okay, we're going to do the same thing for addition. Now, I would recommend if you're feeling like, ooh, I think I kind of got this, like I think I might be able to do the addition part, try to do that. Pause the video. Try to write down a justification in this sort of form for addition. Because if you can do that, and then you can compare it to mine and it looks similar, that'll be great. If you're feeling like, whoa, this is way too much, great. The addition will look very similar, and so maybe it will clarify a few things. And there's an in between here, right? You could start trying to write out an answer, right? Like, and maybe you would get to like something like this point, and you would say, okay, I don't know what to do. That's fine too, right? See how far you can get before you feel like you're kind of just guessing things. All right, so let's look at addition. It's going to be the same sort of idea, but instead of taking a real number and a vector in the set, we're going to take two vectors in the set. And I'm going to call them v1 and v2. I could have called them v and w, that would be fine. But I'm taking any two vectors in the set. And again, I have to then say, well, these have properties. Right, if v1 is in the set, then I can write it in the form x1, y1, z1, such that these three coordinates add to 0. But I can also write it, or sorry, I can also write v2 in the same form. So I've taken two arbitrary vectors from the set. Arbitrary meaning I haven't specified what they are. There could be any vector in the set. I've clarified what that means for them to be vectors in the set, and now I'm going to see what happens when I add them. When I add these two, well, the whole point of writing them out in terms of their coordinates was to add them up. So I'm almost done. I'm trying to show that this thing is in the set, and the defining characteristic of the set is what happens when I add up all the coordinates. So what happens if I add up all these coordinates? If I rearrange this, because addition is associative and commutative, I can put the x1s, the y1s, and the z1s together. That doesn't change what they add up to. And I get 0, which is what I wanted. So this means what I've shown is that v1 plus v2 is an element of T, and T is closed under addition. All right, so I'm going to finish up the proof. There can be this temptation in any problem, whether it's math, physics, kind of, I don't know, in English paper, I assume as well, though I don't do quite as much of that. Make sure that you do the easy work. We've just done a ton of hard work, and we should do the easy work of writing one final sentence to clarify what we mean. We did all this legitimately hard work, and what did we do here? We showed that 0 is in the set. It's closed under multiplication. It's closed under addition. And so I should just reiterate that at the end, right? Like, you don't want to lose points on an English essay because you don't sum up your argument that you've spent a lot of time writing. I don't want to make my proof unclear. Since T contains 0, and is closed under addition and scalar multiplication, T is a subspace of R3. All right, so that's a full proof that T is a subspace of R3. I showed that the zero vector satisfies the defining condition. I showed that if I started with any scalar, any element of the real numbers, and any vector in T, that I would get a vector that was contained in T. And I showed that it's closed under addition. That if I started with any two vectors in T, when I add them, I get something that's still in T. And so this is a subspace. So I know this has been a long video, but I think this is a hard process. So I think it's something that you need to spend time on. And what I want to point out is that we have this experimentation phase, right? When we're trying to do this, we have the experimentation phase, and this is the same no matter what the answer ends up being, right? We're writing down examples, we're looking for patterns. If we find a counterexample, we go off in one direction. If we find a counterexample, we can like sigh and just say, oh, good, this is going to be easy. If we find a counterexample, our proof is straightforward. Our proof is literally just presenting that counterexample and adding some words so that someone who's looking at it understands what you're saying, right? Like as I said, if I leave off this last sentence, someone looks at this and says, cool, why are you telling me this? And then I say, oh, right, I'm telling you this because I'm telling you that the set's not closed under addition. So if you find that there's a counterexample, your proof is straightforward. If you don't find a counterexample, you notice patterns, your proof is much harder. And in the end, your proof doesn't use any of your examples, right? We can't do a proof by example. That's not a thing. That's not what a proof is. But what's important is to not fall into the trap. There are two possible traps here. We can't do proof by example. So if you realize something's a subspace, it is never enough to present examples. For the zero vector, you do present an example because there's just one thing you're looking at. We're only considering one vector. But for scalar multiplication and addition, we cannot just present examples. That does not constitute a proof. The other thing that you can do, a mistake I see a lot of, which is understandable, but you definitely want to avoid because you're making your life harder, is let's say you start trying to write one of these proofs, right? And you start to do something like this and your algebra gets messy. If your algebra is starting to get messy, you should start being worried that maybe you're trying to prove something that's not true, right? Maybe actually the thing you're trying to prove is untrue. Maybe this is not a subspace. So for instance, in this example, and I'm not going to go through this, we could have tried to prove that S was a subspace of R3 in the exact same way that we did before. And if we tried to show that S was closed under addition, we would get some ugly multiplications of stuff. That's what would end up happening. And we would have some algebra that kind of didn't seem like it was working. That is not a proof that something's not a subspace. So if you realize something's not a subspace, either because you found a counterexample or you're starting to realize that the proof you're writing isn't going to work, you have to go back and find a counterexample. Showing something's not a subspace is always going to be done by counterexample. It's not enough to say our algebra is really messy. But that's actually a good thing, right? In some sense, in the sense that this is the easier type of proof to write, right? If I give you an example and ask you to prove that it's not a subspace, that's the easier proof to write out once you've done the hard work of figuring out what your counterexample is. Okay, so hopefully those were helpful, because again, I think this is a very challenging type of problem, especially if you're not that familiar with proofs. What I'd recommend is, if you're struggling with this, try to model your proofs off of mine, right? Try to figure out exactly what I'm doing and try to take what I wrote and then translate it into the language of the specific example you're working on, because often that's the step that you need to get a better understanding of something, right? When you saw what I did, it kind of made sense, and then you apply it in a different situation and you're forced to fill in the details. Those details, I think, are often what gives you the understanding of how this works.